Good afternoon, everyone. Hope we've all had a nice week. Get a bunch of good astronomy work done in the past couple of days, I hope. Let's see. So just to quickly recap, last week we were talking about light and how we use light as a tool to help make sense of the universe and everything that's in it. Particularly because we can't go to distant stars or distant planets. There are places that we just don't have access to because we don't have the technology to get there. So light's an incredibly useful tool for us. There's a very broad electromagnetic spectrum, right? And within this spectrum, there are different types of light dependent on the wavelength and frequency. And every single element, every bit of matter that we know, hydrogen, helium, carbon, oxygen, nitrogen, so on and so forth, every single one of those elements has its own unique chemical fingerprint, which has to do with that element's ability to absorb and emit certain colors of light. And so that we can look at distant objects and look at the light coming from them, and based on what kind of light we're receiving, we can make inferences about what that object is then made of, even though we have no means of getting there, right? So just by looking at the light. So one, we can tell what things are made of, but light is also useful in looking at how things are moving relative to us. Because when an object that's emitting or reflecting light is moving towards us, the waves of light as they approach us are smushed together. And it causes the color or the frequency of that light to increase, right? And so something that is normally green that's moving towards us very fast might appear slightly bluer than if it were stationary. And something that's moving away from us would have its waves stretched out a little bit, and there would be a lower frequency, and that kind of light might appear redder than it normally does. So light is an incredibly useful tool for understanding things that are far away, but how do we understand our own planet, right? Something that we do have access to studying, right? We can interact with it in a very tangible way. So I'm gonna open up my slides here. Let's see, there we go. Okay. All right, everybody, we can see these screens. Any issues here, anyone? All right, I'll take that as my sign to go on. So today we are going to be talking about Earth's interior structure, how we can compare that interior to the interior of other planets. How do we even know what the interior of the Earth looks like? How far into our own planet have we actually explored? We'll look at magnetic fields and a planet's ability to produce a magnetic field, why magnetic fields are useful for a planet and for life on a planet. And then we'll go on to exploring the different atmospheres of these terrestrial planets. We'll talk about what terrestrial means. And if there's time today, we'll talk about Jovian planets as well, This is for the afternoon and evening sections. So this is everything that's going to be taught throughout the day today. Okay, so in looking at our solar system, right, there are, we're gonna talk about how the planets formed. That's going to be a major theme that we talk about. If not today, we'll talk about it next week. But there's an era. Oh, you know what? Did I skip something? Give me 1 second, folks. 1 second. Okay, sorry everybody. For anybody that's watching this recording right now, I had the wrong slides open because I mislabeled them in my Finder on my computer. Okay, I knew I was like looking at the stuff that was coming up in the slides. I was like, I don't think I talked about anything that would have gotten us this far. We skipped over a lot of important things before we got here. So here's what we're going to talk about today. We're going to talk about why we put telescopes in space. We're going to talk about what our solar system even looks like. We're going to talk about how we can explain the properties of the solar system. And then we're going to look at something called nebular theory, which is a theory about planetary formation. And that's going to lead us into next week's lesson, which is going to be on exploring Earth's interior and learning a little bit more about each specific planet. Okay, sorry about that, everyone. So here we go. When we look out in space, right, the tools that we use are called telescopes. But I'm sure we all knew that already. There are issues with telescopes. There are different kinds of telescopes too. There are telescopes that use lenses to bend light in a way that allows us to produce an image. So to take something that is very small and very far away and magnify it. But we can also do something similarly with mirrors. Both types of telescopes have their pros and cons. With a lens-based mirror, one of the issues that you encounter is something called spherical aberration, which makes the image fuzzy. So what exactly is spherical aberration? What does that even mean? When light enters from one medium to another, so when light goes, let's use the example of a prism, because we talked about a prism last week and how prisms disperse white light into its constituent colors. When white light enters a prism, all of the different colors that make up white light bend, but they all bend slightly differently. And that's why they become separated and we see a rainbow. When we look at light coming from a distant star, the light that we're seeing doesn't necessarily just have to be one color. It could be a combination of wavelengths that give us some final overall color. And as that light enters a curved lens, right? Lenses are curved. They're not flat. The different colors of light coming from a particular point in the sky can bend slightly differently, and it makes the images fuzzy. So one of the issues with having a lens-based telescope is that it can slightly distort the image and decrease your resolution, right? How much you're actually able to see. And so why do we put telescopes in space, right? Like the Hubble Space Telescope. Why do we put these telescopes in space and not just leave them on Earth's surface, right? Many people think that having these telescopes closer to the stars is going to make it easier to see the stars, and that's not actually true. That's a very common misconception, though. Does anybody think that they know why we put telescopes in space? I'm looking for that class participation today.
Shot in the dark, it reflects light better, so we won't get light pollution from our Earth.
Okay, so it's not that it reflects light better, right? The purpose of the telescope is not to reflect light elsewhere, right? The purpose of the telescope is to capture light. And now that sort of puts us on the right track with what you were just saying, Ed, which is that if we're trying to capture light from outside beyond our planet's atmosphere, we don't want to be looking at light from within our atmosphere, right? We want to avoid looking at light from Earth. We want to look at light from distant objects. So one issue is that we get light pollution. And I'll go ahead and I'll just jump to that slide here. There are certain places on Earth where it's easier to make observations of the night sky than others. You know, you'll notice if you ever see people in the pictures like camping in the desert, beautiful view of the nighttime sky. You can see the Milky Way galaxy. But from here in New York, when we look up, we can, you know, you'd be lucky if you could count 10 stars because there's so much light pollution. Light that's coming from the surface is going up towards space, but then bounces back because it's hitting particles in the air. Right, so that's what we call light pollution. Makes it very difficult to see things. Right, so like you'd want to go somewhere that does not have a lot of light pollution if you want to get a really good view of the night sky. So like most of Africa, large parts of like South America, if you're looking like the Amazon. You could look at Australia, so on and so forth. All right, there's another reason that we tend to want to put telescopes in space. It's because, set aside light pollution, the Earth has an atmosphere. And that's a problem if you're trying to observe light that's not nearby, right? Because our atmosphere has turbulence, right? Our atmosphere is constantly moving, right? Our atmosphere is made of parcels of air that rise and fall. They get hot and cold, expand and contract. And as light travels through those parcels of air on its way to the surface, that light bends, right? The path that the light takes slightly bends and jiggles. So, when you look up at the night sky, actually, let me start that question over. How many of you prior to this class would say that stars naturally twinkle? No matter where you are, whether you're on Earth, whether you're in this International Space Station, whether you're on the moon, if you look at a star, you would see it twinkling. I imagine probably all of you, right? But stars don't really twinkle. At least not from anything that they're doing on their own, right? Stars only appear to twinkle because as starlight, which is like a very, very, a star is a tiny point on the sky, right? So if light from a tiny point has to pass through Earth's atmosphere and the atmosphere is constantly moving around, it's going to jiggle and make that star appear like it's moving or flashing a little bit. So stars don't actually twinkle. That's just the result of Earth's atmosphere and the turbulence, right? Again, turbulence is like what you experience when you're flying in a plane and the plane starts to shake. It's because the atmosphere is not uniform. There is another issue with ground-based telescopes. Yes, Barrier.
Oh, sorry, I was going to say the same exact thing before you went to the slide. I feel like you will have more like options to move around that rather than just being grounded in one area. And you will have more like, like you don't have to worry about anything passing by as well, I guess.
Well, so it actually has nothing to do with being able to change where you are. Because once you're in space, it doesn't,
Oh,
You
no,
can
I
just look any
understand,
which
but
way.
like, I understand that. Like, I'm talking about like, let's say, let's like, you're gonna have like, the option of looking at 180 degrees or whatever you're looking at, like like the upper version of the sphere. So when you're up in the sky, I guess you'll have like a little bit more angle movement or something like that.
So
Not sky, I'm the atmosphere, I mean, or
So
above.
that's not really one of the main reasons. Also, it's not like telescopes like quickly are turning around. Usually when a telescope's in space, it's looking at one object for a very long period of time to try to
Oh,
capture
okay.
as much light from it as possible. The real problem with having a ground-based telescope is that not all light from the electromagnetic spectrum actually makes its way to Earth's surface, right? So a lot of like gamma rays, X-rays, most ultraviolet light gets reflected by our atmosphere. It's not or absorbed. It doesn't actually make it to the surface. So we talked last week about how light is so important, especially the different parts of the electromagnetic spectrum, the different kinds of light are so important for getting a full picture of what's happening in the universe. If we're on the Earth, if we're on the surface, we're not able to access the X-rays and gamma rays from distant objects because they never make it to the surface. So by placing a telescope outside of the atmosphere, we're now able to gather that kind of light. Whereas on Earth, we couldn't gather it. Right? So you can see here, like radio waves make their way to the surface. Some infrared does, a lot of infrared does not. All visible light makes its way to the surface. Some ultraviolet light makes its way down, but most X-rays and gamma rays do not. Right? So by putting a telescope in space, we're able to, bypass Earth's atmosphere. We don't have to worry about it, absorbing some of the light that we're trying to capture ourselves. Okay, so that being said, space telescopes are very useful to us, right? We like putting telescopes into space. It overcomes all three issues. It overcomes light pollution, it overcomes turbulence, it overcomes not all light transmitting to Earth's surface, right? So that's why we put telescopes in space. Now, that being said, we do have telescopes on the ground, but how accurate are they? We see these like big observatories. Can they really look at stars and really look closely and carefully at what they're doing? Or do we just see a whole bunch of twinkling? Well, we have a tool that allows us to overcome that. It's called adaptive optics, right? And so adaptive optics is basically a way of looking at how much turbulence there is in a certain region of the sky and adapting our mirrors, right? If we're taking light from a mirror and we're reflecting it back into our eyes to magnify the size of the image, or to magnify the size of the object, we basically have a way of warping the shape of the mirror to account for the distortion of the atmosphere. So we use lasers like this orange one to create an artificial star in the sky. Not actually making a star, but we're creating a point in the sky that looks like a star. And we know what that point should look like because we're the ones creating it. So as we watch that point, as we watch this laser and the artificial star it's creating, we can see how the atmosphere is playing with the light. And based on that, quickly adapt the surface of our mirror to bend the light back into the correct shape. So for example, here's an image of Neptune with and without adaptive optics. Right, without, it's all fuzzy, it's very low resolution, but with it, you can very clearly see, patterns on its surface, things going on in Neptune's atmosphere. Right, so adaptive optics are very, very useful. All right, any questions so far? Okay, moving on. So to summarize what we just talked about the last 20 minutes or so, all right, we put telescopes in space to pretty much avoid all the issues related to Earth's atmosphere. Right, that light gets absorbed, that light gets distorted, and that we have to deal with light pollution from light on Earth. Right, so it's the ability to look at the universe in all of these different parts of the electromagnetic spectrum that allows us to get a full picture. Right? All of these different rows, all of these different kinds of images are of the exact same object. But you'll notice that as you go from picture to picture, they look different depending on what kind of light you're using to look at it. And each one of these tells us a different part of the story. Right? So it's not unless we're looking at the universe in all wavelengths that we can really paint a full picture. Right? So let's move on. We're going to talk about now the planets in our solar system, and we'll briefly touch on the sun as well. So we have two categories of planets, and each category has four planets within our solar system. So we have terrestrial planets and we have Jovian planets. A terrestrial planet is a planet that is rocky, right? That has a solid surface. So Venus, Mercury, Mars, Earth. That was not in order from the sun. That was just me naming them. In order from the sun, that would be Mercury, Venus, Earth, Mars. They are all rocky planets. Notice in this image, Mercury, Venus, Earth, and Mars are relatively small compared to the other four planets in our solar system. These are the gas and ice giants. They are the Jovian planets. Jovian means Jupiter-like, planets like Jupiter. So we've got Jupiter here, Saturn, Uranus, Neptune. And then at the end, there's Pluto, which is technically not a planet, but it's a dwarf planet. So what similarities and differences do you notice? What are some things that you're seeing as you look at this?
I'm noticing that Jupiter and Saturn are the largest, and that's because I think they're both gas planets, whereas Uranus and Neptune are both ice planets.
Okay, gas and ice, right? It's not just ice.
Oh,
but also gas planets, right? What other similarities or differences do we notice? We can talk
I mean, I'm gonna say something that's obvious, I guess. I guess the further they are, the more solid ice I'm assuming it will have. I don't know.
Well, not. You can't quite tell that from the image. I want just focus on what you can see. What are some direct observations you can make by looking at this picture? Because you can't quite tell what they're
The
made
colors.
of. Okay, what do you notice about the colors?
The Saturn and Jupiter, they're both like muddy clay color, where Uranus and Neptune are both hint of blue.
Yeah, they're both bluer in color, and Uranus and and Saturn and Jupiter are both kind of like reddish, beige, brownish. They're kind of like yellow. Okay, what else? So aside from color, What else could we comment on? What else could we comment on?
Both Saturn and Jupiter look like they have an atmosphere compared to Uranus and Neptune.
What do you mean it looks like they have an atmosphere? What does an atmosphere look like?
Like it looks like it has built up gas trapped in like surrounding the planet.
Neptune doesn't look like it has doesn't look like it has gas on it.
It not from the picture, I guess.
Does Earth?
Well, you could kind of see the white clouds.
Does
so-
Venus?
Oh, okay, never mind.
Does Mars? Right? That's what I'm saying. Like you can't quite say that. But there are other things. Like what are some obvious things that we could compare? Color. We could compare size. We could compare. Yes.
Sorry, the ring of Saturn. I think that's the biggest difference that I see is that Saturn has a ring around it.
Saturn has the most pronounced rings, but Saturn is also not the only one with rings. This image is just not high resolution enough to capture that. But we will talk about that. Yeah, Saturn does have a very obvious ring, right? That's different from pretty much everything else. What else? What's another big difference between the inner planets and the outer planets?
They're more uniform. The I'm having difficulty saying the word. The T1 is more uniform in size, whereas the one
terrestrial,
yeah. The Jovian ones are clearly bigger, but only two are kind of similar in size, whereas the other two are similar in size, but compared to the half of them are different.
So if you're just saying here's how the terrestrial planets are different than the Jovian planets, what would you say, Ed?
They're smaller and
done.
Yeah,
that's it. They're done. They're smaller, right? But also the terrestrial planets are closer, right? So the 4 closest planets are also the 4 smallest planets. And the 4 largest planets are also the 4 farthest planets, right? So there's some type of correlation there, perhaps. All right, let's move forward. So let's talk about the different objects in our solar system. And let's not forget the sun is here. The sun is enormous. By the way, this is not a scaled diagram in terms of the distance between objects, but this diagram is scaled correctly in terms of their size. So if you're comparing the relative size of Earth to the relative size of Jupiter, this is the appropriate size difference. However, this is not the distance between the Earth and Jupiter. All right, so let's start with the sun. You have a comparison here, the size of the Earth compared to the size of our sun. Sun's a whole lot bigger. Of all of the mass, right? Mass is like a measurement of how much stuff something is made of. Of all of the mass in our entire solar system, 99.8% of that mass is in the sun. The sun is made of mostly hydrogen and helium plasma, right? Which is a kind of ionized gas, meaning it's electrically charged gas. It's not electrically neutral. Like the oxygen around us is just regular gas. It's electrically neutral, right? The air around us. Plasma is not. Plasma is like the stuff that you see inside of those like little it's called a plasma ball, right? It's like the little orb with like the streams of electricity coming to the glass surface. And our sun is constantly converting mass into energy. And that's why our sun glows and is so bright. It's burning mass and creating energy with it. All right. Then we've got Mercury. Mercury is made of mostly metal and rock. It has an incredibly large core, and the core is made of iron. The planet has no atmosphere at all. It is completely desolate. There are tons of craters all over its surface. It has very steep cliffs, right? Long cliffs, tall and steep. It's like if you can, oh, excuse me, Mom. If you can look in this picture here at the bottom left, you see how this this crater has this light looking line cutting through it. That is a cliff called an escarpment. And we're going to look more at that later. And it's very extreme temperatures on Mercury. Right? So it goes from incredibly hot temperatures of 425 degrees Celsius to negative 170 degrees Celsius at night. Why do you think? I mean, that's an extreme change, right? It doesn't even get that cold on Earth. Remind you, Mercury is much closer to the sun. So how does that make any sense? How can a planet that's much closer to the sun be colder than Earth?
It has no atmosphere, as you said, so it doesn't hold in the heat.
Correct. And no atmosphere to hold the heat in, right? So it's very, very hot. You know, you could bake a lot of food. 425 degrees Celsius. You know, go ahead, convert that to Fahrenheit, which is how most temperatures are given in the United States. And it's going to be larger than that number. It's going to be a very, very big number. Then we've got Venus. All right, of the terrestrial planets, Venus is the closest in size to Earth. But from space, it's hard to see. You can't see Venus's surface. It just looks very cloudy. Venus has an incredibly thick atmosphere. And this atmosphere is due to a runaway greenhouse effect, which traps a lot of heat, right? So much so that the temperatures are even hotter than Mercury, both during the day and at night. 470 degrees Celsius is the average temperature. So just goes to show you how proximity to the sun doesn't fully account for a planet's temperature, right? There are other factors. Moving on. Then, of course, we have our pale blue dot, which is the Earth. Earth is very different from the other planets in our solar system. It is, as indicated there in that first bullet, an oasis of life. Nowhere else in our solar system is there evidence of life. We are also the only planet in the solar system to have liquid water at the surface. That's not to say that other planets don't have liquid water. It's just not at the surface of the planet. Earth is also unique because while other planets do have moons, the typical size difference is much more extreme. You know, you can see there on the right, the Earth and Moon to scale in terms of their size. That is not the correct distance from the Earth to the Moon, but size-wise, you can see how the Moon's actually pretty large, right? By comparison, it's not larger than the Earth, but it's pretty large. Now let's move on to Mars. Okay. So Mars kind of looks Earth-like, right? It's very rocky at the surface, but it's got very little atmosphere, right? At least not one that could sustain life like what we have on Earth. It's also going to be very cold on Mars. Very, very cold. right? Because it has such a small atmosphere, not a lot of heat is trapped. Mars has volcanoes, it has canyons, it has polar ice caps. There is ice on Mars's surface, but not liquid water. It's too cold for liquid water, right? And we have evidence. We can see like ancient river channels that water once flowed on Mars. So is it possible that there could have been life? Maybe. Maybe one day we'll find out. Brings us to Jupiter. Way farther, all right? It's way farther than any of the 4 inner planets, by comparison at least. Now, what makes Jupiter different is that it doesn't have a solid surface to it. It has a liquid surface, a gaseous surface, and that liquid is not water either. It has mostly hydrogen and helium in terms of its overall composition. There are other elements too, but primarily hydrogen and helium. It is much larger than Earth, just in terms of mass. It has 300 times the mass of the Earth. And it has many moons and rings, right? You can't really see the rings of Jupiter. They're not as well known as the rings of Saturn, but they are there. Now, we're not going to talk too much about it right now, but we are going to spend a bit of time later on in the course talking about Jupiter's moons. Because Jupiter's moons, at least the 4 Galilean moons, right, the ones that Galileo saw through his telescope, are large. They're similar in size to the Earth, right? And so there's a lot of interesting things that happen on these moons, and you can see here. I've given the names and some fun facts about them. It's like Io is the most volcanically active object in our entire solar system, even though it's just a moon. Europa has a bunch of liquid water. It's just not at the surface. There's a subsurface ocean. So is it possible that there's life in the oceans of Europa? Maybe. Could be possible. Maybe one day we'll get to go and do some research there. Then there's Ganymede, the largest moon in the solar system, and then Callisto, which is a giant ice ball. That brings us to Saturn, the 6th planet from the sun. Like Jupiter, it is a gas giant. It is best known for its rings. Right? It is the crown jewel of our solar system. It also has many moons. And when I say that Jupiter and Saturn have many moons, I mean upwards of 50 moons, right, where Earth has 1. So there is a spacecraft that is studying Saturn. That is the Cassini spacecraft. Perhaps somebody here will choose the Cassini-Huygens mission for their space mission assignment. That could be cool. Titan is right here. Titan is also an interesting moon because it has an atmosphere. Right, a moon that has an atmosphere. Right? Like what else? What goes on Titan? Continuing on to Uranus. Uranus also has rings. Right, it's smaller than the 2 gas giants, but it is still much larger than Earth. It is made mostly of hydrogen and helium gas. And it's also, I mean, so are Jupiter and Saturn. So what makes Uranus different is that it also has a lot of hydrogen compounds. A compound is a molecule that is a combination of elements, right? So a hydrogen compound is specifically hydrogen mixed with other things. So does anybody know, without looking it up, what these 4 chemical symbols or these 4 molecules stand for? What is H2O?
Water.
That's water. What is NH3? Okay, I had a feeling that's where I would lose people. Alex, you think you know?
Is that nitrogen?
Well, N is nitrogen, but when nitrogen is paired with 3 hydrogen atoms, when they form a molecule together, that is called ammonia. Ammonia. And then there's CH4. CH4, a carbon atom combined with 4 hydrogen atoms. Any idea what CH4 is? Methane. Very good, Alexa. Sophia, you heard that it rotated counterclockwise unlike other planets. Are you talking, I'm sorry, I missed that. Was that on Venus? Yes. So Venus, it's the other way around. I mean, I guess clockwise or counterclockwise depends on your perspective. But typically when we look like from a north, like a down onto the North Pole perspective, like a bird's eye view of the North Pole, everything we see moving around counterclockwise, and Venus actually rotates clockwise on its own axis. But I'm glad that you knew that there was a rotational difference. It's very good. Uranus is also a very interesting planet in terms of its rotational axis because it is extremely tilted, right? Like if this were Earth, we'd see that the tilt is like 23.5 degrees. This planet is basically on its side, right? You can sort of see the axis of rotation because of the rings, right? So it's rotating sort of this way, which means that my mouse here is probably pointing along the rotational axis, right? So it's very, very tilted, which means that there are extreme seasons, extremely hot summers and cold winters by comparison to a planet that is less tilted. And then there's Neptune. Neptune, very similar to Uranus, except it doesn't have the crazy axial tilt. It also has many moons, which is a characteristic of these. What's going on there? Which is a characteristic of these Jovian planets. One of its moons is called Triton. Right? And I know that I already blocked this off, but which of the following correctly identifies characteristics of a terrestrial planet? Well, terrestrial planets are very dense because they're so rocky, right? Those rocky materials are very, very dense materials. They also contain very little hydrogen and helium gas. The terrestrial planets have no rings, they have very few moons, and they have a solid surface, right? Basically, think of Earth. So then, which of these, A, B, D, or E, represents or identifies characteristics of a Jovian planet? Which of these represents a Jovian planet? A, B, D, or E? Yeah, very good, Sophia. Right, it is choice B. Right? Because they're made of mostly helium and hydrogen, they're not very dense at all. At least overall, they're not very dense. And they have many rings, they have moons, and they have no solid surface. Okay, so we know what all of these objects look like. We have a lot of information on these solar objects, but how do we explain why they look this way? How does a solar system form? Right, so typically when you look at a solar system, it doesn't have to be our own, it could be a distant exo solar system. Typically, you'd find that the planets are very small compared to the distances that separate them. You would tend to see that every planet in that system has its own unique features. But there are some obvious patterns that you could point to, just like with our solar system when we look at terrestrial versus Jovian planets. Okay. So again, what exactly does our solar system look like? Well, we've got the inner planets orbiting in this smaller region around here. All right, so this is like the zoomed in version of what's going on. We got Mercury orbiting around the sun. We have Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune on the outside there. And what you'll see here is if you're looking at the orange arrows, all of these planets orbit the sun counterclockwise from this perspective. If you could zoom in and see the little white line around each planet, the little arrow, you'd see that they're all pretty much orbiting counterclockwise, or excuse me, they're all rotating on their own axes counterclockwise. But Venus is rotating clockwise from this perspective. So there's a lot of uniformity, but not everywhere. There are some exceptions. That being said, when moons orbit a planet, they also tend to be orbiting in the same direction that the planet is rotating, right? Which is generally the same direction that the sun is rotating. So if we were to look at the night sky and find a distant planetary system, planets orbiting a distant star, you would probably, you would expect to see the planets revolving around the star in the same direction that the star itself is rotating on its own axis. Okay. So we would tend to see some type of order, right, going on in terms of the motions. We would tend to see that planets fall into two categories: those terrestrial, rocky, Earth-like planets, and the Jovian, gas giant, Jupiter-like planets, which are very rich in hydrogen. You would also expect to see that there is a region of a planetary system that has a lot of comets and asteroids. And in our solar system, there are three regions where we tend to find things. The red ring there is the asteroid belt. And that is where we find most of our solar system's asteroids between Mars and Jupiter. Right out here, this lighter disk is the Kuiper belt. That's where you find most of the comets in our solar system. And then this less dense looking sphere is called the Oort cloud. The Oort cloud, and that's actually where you really find the majority of comets, but they're just so far away that we'll never interact with them.
Isn't that where most of the dwarf planets are as well?
In the Oort cloud?
Oh, like they revolve around Earth in like in a different way. So like you see, you know how in the previous slide you showed most of the planets were revolving in a disk form, like yeah, and most of the dwarf planets are in like a different opposite of that.
No.
Oh.
No, that's not the case, because there are dwarf planets exist in the asteroid belt. Dwarf planets exist in the Kuiper belt.
Okay. I thought just further than the Kuiper.
No, the dwarf planets, there are dwarf planets that are between Mars and Jupiter. We just don't really learn much about them prior to an astronomy course.
Okay.
But then in addition to those other three, so again, let's just look at the bullet points, right? Large bodies in the solar system have orderly motions. That's number one. Two, planets fall into these two major categories, terrestrial or Jovian. Three, you would expect to find swarms of asteroids, comets in particular spots throughout the solar system. And four, there are exceptions to the rules. right? Nothing fits neatly in a box. And we talked about Uranus's odd tilt. We talked about how Earth has a relatively large moon by comparison to other planets that have moons. We talked about, Sophia mentioned how Venus rotates in a direction opposite that of all the other planets in our solar system. So there are differences. And so what started out as a hypothesis eventually grew to become a theory. A theory is to become a theory, something has to be basically what's the proper way to say this? There has to be insurmountable evidence for something, right? No matter how many times people try to break something down, it still holds true. That's what makes something a theory. So nebular hypothesis became the nebular theory of planetary formation, of solar system formation. And the two people that sort of spearheaded this hypothesis were Immanuel Kant and Pierre-Simon Marquis de Laplace. And so let's talk a little bit of physics, okay? So there are certain laws in physics that govern how things in the universe behave. Laws cannot be broken, right? There are no exceptions to laws. One law that you might be familiar with that might be the easiest for you to wrap your head around is the idea of the law of conservation of energy. And everybody's heard this saying before. Energy is neither created nor destroyed, it's only transferred from one form to another. Basically saying that there's a total amount of energy in a system, and that energy can't be created or destroyed, but you can change what kind of energy it is. Well, in a similar line of thinking, there's another physical quantity called angular momentum. Now, when we talk about momentum, just regular momentum, you might think of like a car driving down the road, or somebody running, or a big heavy football player, right, running with a lot of momentum. And how having momentum depends on how fast you're moving and how heavy you are, how much mass you have. Angular momentum is kind of like that, but having to do with rotational motion as opposed to running in a straight line. So something that spins has angular momentum. And angular momentum depends on two things. It depends on how fast you're spinning, and it depends on how distributed the mass is from the pivot, from the place where it's spinning around. So how many of you have seen an ice skater before take their arms and bring them in when they jump and do a spin? Do you all know what I'm talking about there?
The ones that turn like really fast over and over.
Yeah, exactly. Right? How an ice skater is like spinning, or going straight, and then they jump in the air and they start to spin, and then they bring their arms together and their rate of rotation rapidly increases. All right? By bringing the mass, so your angular momentum is the product of two things: your rotational speed and your distribution of mass. If your distribution of mass is high, you can have, and you have a low, hold on, let me back up for a second. I'm saying this in a confusing way. Angular momentum has to be conserved. So let's say that you have an object that has its mass very largely distributed and it's spinning slowly. As it collapses in on itself, right, the distribution of mass gets smaller. right? There's a lesser distribution as it becomes more condensed. But the angular momentum can't change. Well, angular momentum depends on the distribution of mass. So if the distribution of mass goes down, how can the angular momentum stay unchanged? Well, the mass just has to spin faster, right? And so, like, I'll try it on my chair. I'm probably gonna look incredibly silly doing this, but I'll do it for you guys. I'll take a textbook or two, and I'm going to spin myself around. I'm going to take these two objects, these two books, and I'm just going to hold them kind of out so that I've got a big distribution of mass. I'm going to start spinning myself, and then I'm going to bring the books into my chest and see how that affects my rate of rotation. Okay, so let me start spinning. I can't promise that this is going to be really good, but you can sort of see how fast I'm spinning right now. And then I bring this in and I sped up. Did we see that? Could you tell? Could you tell?
Not really, but appreciate the effort.
Okay, well, you can look it up, all right? You can look up a video of conservation of angular momentum demonstration or something like that. In any case, so the hypothesis that Kant and Laplace had was that our solar system was born from a giant cloud called a nebula, hence the nebular hypothesis. And these, there are nebula all throughout the universe, and these nebulae, these giant clouds of gas, are slowly rotating, very slowly. And then if they contract, what happens is they start to speed up, right? So you can see here that as the nebula gets smaller and smaller, right, as it collapses in on itself, the rate of rotation increases, right? As that happens, a couple of things begin to occur. One is it starts to flatten out into a disk, right? Much like a pizzeria, you watch somebody create the dough, right? They take a ball of dough, that's like your gas cloud, and then they start spinning it. And as they spin it, it starts to flatten into a disk shape and widen. But also what happens in this disk is that all of the material is spinning in pretty much the same way. And that's why we find that there tends to be a lot of order in the solar system, right? Things tend to orbit in similar ways. And you've got all these, all of this gas, and the gas starts to clump together. And we'll talk more about that, right? Because it's actually not the gas per se that's clumping, but like the solid material, solid grains of material start to clump together. And as more of them begin to pull on each other with gravity and they clump together, they get bigger and bigger and bigger and bigger. And then you end up with what are called planetesimals, right? Pretty small objects, about a kilometer, as small as 1 kilometer in size. And you can see here that here's a planetesimal that is accreting other clumps and other smaller planetesimals, right? And these planetesimals get bigger and bigger and bigger and bigger. And eventually they get big enough that they form protoplanets. And here you can just, we can see in this image, this is of the, was this the Orion Nebula? Yeah, this is the Orion Nebula. These are different images that we've seen through telescopes of nebulas that are collapsing in on themselves. And sure enough, they look exactly like what Kant and Laplace predicted, right? That you would have like a proto-sun in the middle and a disk of material around it. Look at these pictures, right? Star or proto-sun with a disk of material. Proto-sun, disk, proto-sun, disk, proto-star, disk. And they're, by comparison to the size of our solar system, you can see that they're relatively similar, right? Now, you typically can't see this stuff if you just look at these giant molecular clouds, these nebula. But if we look at this through infrared light, remember we said that different kinds of light give us different images, allow us to see different things, then we can actually see these protoplanetary systems. Here's some more observations in the Orion Nebula. Here's stars forming in the Rho Ophiuchi cloud. Right, and so there are observations that support the nebular hypothesis. Here's another amazing picture. It's amazing because you can actually start to see where the planets are beginning to form. You can actually sort of tell, like, the orbits of these larger objects as they start to accrete smaller things, and they get bigger and bigger and bigger, that they get more defined paths. So it starts to look less like a cloudy disk and more like individual planets eventually that will be orbiting a star at the center. So what have we learned? Well, that as our solar nebula collapsed, it started to spin faster and faster because the angular momentum had to be conserved. The collisions between the gas particles in that contracting thing of gas, that coupled with the fact that it's spinning caused it to flatten out into a disc shape. Right, kind of just think about like pizza dough at a pizzeria. And then in that disc, the small solid particles start to accrete, is the verb, accrete planetesimals and grow and grow and grow into fully fledged planets. Right, so why exactly are there two major types of planets? Why do we have terrestrial versus Jovian in the first place? And this is what we're going to begin exploring. I'm actually going to stop here. I'm going to stop the lecture now, and then I'm going to pick up with that with the evening section. All right, so I'm going to stop to see now if anybody has any questions about homework or anything that they wanted to ask about. If it's related to previous assignments and due dates, I will be changing them. I know that I said that I would do it last week, but I did not, and I apologize for that. So I'll do it today. But aside from that, are there any questions that people were having trouble with? I did address last week that the lab had one or two questions that people weren't able to answer because the simulation just wasn't working. If that is something that you were concerned about, I will not be counting those problems. All right, you do not have to worry about them. All right.
Professor, I have a question about the mission, the space mission. Can you go more into depth with it, please?
Yeah, absolutely. So you're going to be giving an approximately 5-minute presentation on a space mission that has been conducted ideally recently or in the last 2 decades. So there are a bunch of space missions out there. You can go to NASA's website and you can find a lot of information. I'll post some stuff there for you under the space mission tab on Blackboard. A space mission is not just like it, we never just say, let's just go to space, just to say that we went to space, right? We're always going, and these missions are always focused on answering some type of scientific question, right? So what you need to do is figure out what is the scientific or the astronomical question that's being asked by, by the people that are going on this mission, and how are they testing it? When did this mission happen? what's the purpose of it? What are we trying to find? What question are we trying to answer? What are some of the tools that we're using on this mission or through this mission to gather information, right? What kind of information are we gathering? How are we gathering? What are some of the notable things that have happened through the mission? Perhaps you want to explore, or not perhaps, you should be exploring, what was the scientific return, which is like the data that was collected, and then analyze what that data means. So don't just say, this is the data, and then move on, right? You should be able to say, this is the data, what it means is that, and then say, how does that either answer, support or negate what the scientists thought would happen? How does that, help support their scientific question? Are they getting conclusive information that answers their question? Are they not? Are they learning something other than what they thought they would learn? Sometimes we think that we're going to find something, and then we end up finding something totally different, which sets us on a totally new scientific path. So that's something else that you want to consider. And then, and then just sort of report back on what's the current status of the mission? Is the mission already completed? Is it ongoing? Have there been follow-up missions as a result? It's like if you're talking about the Apollo missions, you might say like, look, there was Apollo 11, Apollo 12, Apollo 13, blah, 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 blah. If you're talking about Mars, you might talk about Curiosity, Opportunity, and Perseverance, or you might talk about the different Mars rovers. There's so many different things and space missions. So you can look up, like on NASA's website, you can go to NASA Jet Propulsion Laboratory and look up their different space missions. You can look up the European Space Agency, right? Look at all of their different space missions. You could look at Japan's space agency. You could look at Russia's space agency, right? And see. Well, SpaceX is not really doing scientific missions. They're more acting, I think, as a transportation to and from space, right? Like SpaceX itself is not conducting missions to study celestial objects. SpaceX is all about creating ways to get to and from space more easily, with less and more sustainably, right? Like that's been a focus of like the Dragon rockets, right? That like they are that instead of coming back to Earth after sending something into space and just landing in the ocean and becoming complete waste, that these rocket thrusters can actually land themselves upright and then be reused for another mission. And that's incredible. So hopefully, Alex, that gives you a little bit more insight into the space mission assignment. I will be asking for two other things. So let me actually back up. The last week of class, sorry, my internet connection just became unstable. Can you hear me?
Now it's better.
Okay. So there are three things. One, you're giving a presentation, a 5-minute Zoom presentation. Okay. You'll share your screen, you'll have your PowerPoint pulled up, and you will narrate your slides. I put it in the guidelines, but I'll emphasize it here as well. Your slides should not be filled with text. There should be almost no text at all, aside from the titles of slides. Your job is to narrate over pictures, right? And tell a story of what is going on. All right. Tiffany, I hear your mic is on. Do you have a question?
Yeah, I'm sorry. But I was wondering about that question from.
I will answer that after I finish
Oh, I'm so
addressing
sorry.
this. That's okay.
Sorry, how will you know we're not using the same topic as someone else?
Because you're going to see the sign-up sheet.
Oh, sorry, I didn't see.
You'll see the sign-up sheet. If somebody else put something before you did, tough luck. You can't pick that thing anymore.
Oh, okay, I wasn't aware of that. Sorry.
This is so the final project. This final assignment is going to be due. Is going to be presented during the last week of classes. All right, during week 12.
So this is not due anytime soon?
No, but you need
Oh.
time to put this together.
Okay.
All right, you're giving a 5-minute presentation. You have to do research. You need a works cited page. You need to have a summarizing document that describes what it is that you're going to be talking about in your presentation. Giving me background information. Where are you getting your information from? You need to submit a draft. Submitting a draft is part of the grade, separate from the presentation. All right, if you don't submit the draft, but you submit a final project, you still lose 15 points for not submitting a draft, even if your final project is perfect. Right, there are checkpoints along the way that you have to make sure you're meeting. So the first draft, if you check the calendar, where is it? Share my screen here. Okay. If you check the calendar, all right, space mission signups. I put it back to this week. That's fine. Will be due by May 21st. So you have just over a month to get your presentation drafts in. All right. You'll get some feedback on it. And then during week 12, that's when you're going to be giving your presentations. Something's wrong with this due date though. This should be due on 6/6. That way on 6/7, everybody's presenting. Okay, so that's going to be that. Okay, I think that I hit on all of the points that I wanted to hit on there. Okay, so you can start signing up for the space mission assignment. All right, you can click the sign up link. It's a Google sheet. Everybody's name should be on it. If it's not, let me know and add it. But you should be able to look alphabetically by last name and find your name on the list. Okay, so that's going to be that. Now, Tiffany, I'd like for you to pull up your question. That way we can talk about it. If anybody here, if you want to head out, you can head out at this point. Unless you have another question related to homework that you want to ask. Otherwise, see you later.
Just one more question regarding the presentation. Do we just go in and just sign it right now? How would we tell, like, let's say we sign up now, we all sign up at the same time with our space missions?
Mm-hmm.
That's basically my question. Like, if we're all gonna go now, we all find the same thing. How will we know?
Whoever types it first gets it.
All right.
It's a shared document. You'll see if somebody's typing. You'll know. Yeah, you're not all going to be typing in at the same time, and I doubt you're all going to type in the exact same thing at the same time. I can also go back in and see who typed it first. So
okay, there we go.
I'm not concerned. If you're worried that somebody else typed it after you, I can go back in and look at when they did that. I can also see if you were mistaken. Maybe you typed it in after them. All right, so just be careful when you're looking at the list. All right.
I do have a question. I don't want to get, I know that Tiffany's waiting. Sorry, Tiffany. What about grades? Like, when are you, we're going to be able to like know where we're at with grades?
So the discussion grades, if you are answering the question and you are responding to at least 2 other discussion posts each week, then you should be good with the discussions. You should be earning full credit, unless you're giving like really half-assed answers, and you're not, and you're avoiding your question. As far as the homeworks and labs, you see your grade, right? You should be able to see how you did after you hit submit. It should tell you how many points you earned, right? So you can keep track of all of the, if you're trying to figure out how many, like the percentage of points, right? You can look at the total number of points that you can earn, and then the total number of points that you did earn, right? Divide what you earned by the total and set that equal to X over 25. And that's going to be the percentage or the points towards your final grade. Right, because let me just pull up the, here. Right, on the syllabus, each of these 4 categories is worth 1/4 of your total grade. So if you're getting everything right in the labs, then if you get everything right out of all the, if I don't remember exactly how many points it's out of. If it's out of 90 points, it's not. But if it's out of 90 points and you get 90 points, then you have 25% out of 25%. If you have, if it's out of 90 points and doing quick math here, and you get 63 points out of 90, then you are going to end up with 17.5 points out of, or 17.5 out of 25. So there's a way to keep track, but it's not updating that on Blackboard, and I'm not sure why it's not doing that. So you just got to keep track of how you're doing on the assignments. What's your, I wish there were a way for me to show it. As far as I know, everything that I did to plug it in on Blackboard should make it so that it shows the grade, but it's not. It doesn't even show you the due date. And I can guarantee you that every one of those assignments has a due date plugged in, both on My Open Math and, excuse me, not on My Open Math, but on Blackboard. So I don't know why it's not coming through. I will try to figure that out, Alex. I will let you know if I can get those grades transferred over to the Blackboard gradebook. But so far it's been giving me a lot of issues. So I haven't gotten around to figuring it out. Sorry about that.
Okay, so Professor.
Yeah, can you share your screen, Tiffany? I just enabled screen sharing.
Oh, okay. Let me try. Let me get it.
All right, to anybody that's watching this, I'm going to stop the recording now, and I'll see you later.